Today we're doing some hard questions on the mole concept. These are all past paper questions and they're a hodgepodge, a mixture of lots of different varieties of questions. They're generally on the harder side. And they should give you a type of insight into the tricks that can happen in chemistry. Questions can get pretty hard. And so for this first one, it's asking you to understand what an ideal gas is. And the main thing about that is that you realize that there is no attraction to itself. And so there's no intermolecular forces that we consider. There's other things that you need to know about an ideal gas, like when they collide, they have elastic collisions, which means they transfer energy perfectly between each other and there's no heat loss. But the main thing we're focusing on is their attraction to each other. And if I increase the pressure and they get grouped, pushed into each other a bit more, I shouldn't see any more intermolecular forces because they have no intermolecular forces. They have no attraction to itself. So the pressure and the volume that they stay at should stay constant. Okay, so the answer is B for this one. To explain it, D would be when you push them so far towards each other. So as pressure increases, you're pushing them closer to each other. This is when they start repelling from each other. That's if you jam two particles right close up next to each other, closer than they want to be, they actually start repelling. And this is at extreme pressures. And so this would repel and push away. As they're getting pushed away, they move faster, which means they would hit the walls with more force, which means, if you don't know, pressure equals force per area. And so if they're moving about faster, they'll apply more force per area on the walls of the container. And so pressure and volume, so pressure will go up and you'll go above an ideal gas. And this is attraction, the opposite. This is when you group them together and because you've clumped them together, you have allowed the attraction. What does a real gas look like? Well, most real gases, when you push them close together at low pressures, they start to attract each other. But if you push them too close to one another, they start to repel. Okay. All right. That's a bit over-explaining, but most people can just recognize that an ideal gas shouldn't be affected by pressure and should stay constant. For the next question, we've got the molar mass of a gas with a density of 5.8 grams per litre at 25 degrees and 100 kilopascals. First things that come to mind for me is I know that the formula for density is mass on volume. I don't know if I need to use it. Useful to know. And anytime I see 100 kilopascals and 25 degrees, I know this is molar volume. And for this particular one off my data sheet, it's litres per mole. Now, I got to get to molar mass. I can kind of see from my units, which is, I've got the advantage, I guess, 5.8 grams per 1 litre. And I got to get it into grams per mole. And I can see how this one's litres per mole. So if I go times by 24.79 litres per mole, I'm going to get a cancellation of the litres and be left in grams per mole. So I really just need to plug in 5.8 times 24.79 and I get 143.782 grams per mole, which is the units of molar mass. And I see the question says closest to, and it is that. Now there's two sig figs, so it's not a very good question in terms of significant figures. I'm just going for the closest answer. How many moles of the sodium ion are in 20 mils of 0.4 moles per litre? This is molarity. This is moles per litre or moles per litre of sodium phosphate. And you may notice that there's 3 sodiums in here, so 3 sodiums. What you need to understand, this is a ionic compound. It's dissolved in water. It's in ion form. So when one sodium ion splits apart, you get 3 sodium ions and 1 phosphate ion. So one big particle splits into 4. And so I got to go moles of my sodium ion. It's going to equal 3 times the moles of sodium, how many particles I have of sodium phosphate. So I've got to work that out through C times V. So it's going to be 3 times the concentration times by the volume in liters, so 0.02. That should be my answer in moles. So I got 3 times 0.4 times 0.02 is 0.024. Okay, and I expect that is the dummy answer by not times it by 3. Moving on. The airbags in cars contain sodium azide and an excess of potassium nitrate. In a car accident, the reaction shown below occurs, producing nitrogen. This causes the airbag to inflate rapidly. How many moles of nitrogen gas are produced in total when 1 mole of sodium azide decomposes in an airbag? How many moles of nitrogen gas are produced when 1 mole? That's a repetition again. Right. 1 mole of sodium azide. So if 1 mole were to react, then I would get 1.5 moles of sodium azide dividing by 2. So all I've done, is divide this by 2, divide that by 2, because I'm only interested in nitrogen. So, but then that also, this guy further decomposes and makes some more nitrogen. So if this reaction didn't happen, I'd be locking in 1.5 moles. However, the trick in this question is that this sodium further reacts with the potassium nitrate and produces more that. So if I had 1 here, I would get 1 mole of sodium. That 1 mole of sodium would produce 1/10 that, because I have to divide by 10. And so I would have, well, another way to put that is 0.1 is 1/10. And so my moles total is 1.5 plus 0.1, 1.6. This would be a very hard question, by the way. Yeah, it's just using molar ratios, but in a very confusing way. What is the number of oxygen molecules in the 2.5 grams of oxygen inhaled by the average person in 1 minute? Right. Okay. I need to get the number of molecules, which is like the number of particles. And I'm going to have to eventually use this formula, which is not a very common formula. It's like if you know Avogadro's number, this is Avogadro's number. Avogadro's number, which is 6.022 times 10 to the 23. All you're saying is that you got some kind of ratio of that. If you had half the particles, if this was 0.5, it would be half of 6.022 times 10 to the 23. So it's some ratio of how many particles are in a mole. I also know that I get given mass, and that's going to enable me to work out moles. So moles of oxygen equals mass on molar mass equals 2.5 divided by 2 times 16. And that's going to be 2.5 divided by 32. That gives me 0.078125 grams. Mole. I should say mole. And that's like a seventh of, 7% of Avogadro's number, more closely to 8% of Avogadro's number. So I'm just going to plug that mole up here, and you get 0.078125 times 6.02 times 10 to the 23, and that's going to give me my answer, which is 4.7046 times 10 to the 22, which looks like that. The bromide impurity in a 2-gram sample of a metal nitrate is precipitated as silver bromide. Silver is always +1, by the way, so it's silver bromide. If 6.4 mils of 0.2 moles per liter silver nitrate solution is required, what is the mass percentage of bromide in the sample? Okay, so I got to work out the moles of bromide, I should say, and I'm going to have to get that from this. So what you probably first need to understand is the silver ion is bumping into one bromine and making one silver bromide. So in this reaction, this is the actual reaction that takes place. Nitrate would be called a spectator ion. This is all 1-to-1 ratio. So this makes it very easy. So if I'm to figure out the moles of bromine, they're going to be equal to the moles of silver that I use. And the moles of silver that I use is going to be equal to the moles of silver, the amount of particles of silver nitrate that I put in. And that's going to be C times V, 0.2 times 0.0064. And so you got 0.2 times 0.064, that gives me 0.00128 mole. My mass of bromine is just simply that times its molar mass, which from memory is 29.9. 79.9. Just double check that. Yep. 79.9. That gives me a convenient number of basically 0.12. Right, and so that's the amount of bromine that is in my 2 gram sample. What they're asking is for percentage mass. So what I need to do is go for the percentage of bromine in the sample. Should have bromine minus. It's going to be the mass on the mass of bromine on the mass of sample, I guess, mass of the metal nitrate. Mass, I'll just call it mass total. And times by 100%. So I'm going to get 0.1022 divided by 2 grams times by 100 divided by 2 times equals 100 equals 5.1136%. 5.11, easy. Okay. In an experiment, 5.85 of liquid ethanol was ignited with 4.2 grams of oxygen, assuming that the reaction was initially carried out at room temperature. Okay. Because it says room temperature, I'm kind of feeling like I'll use molar volume somewhere, although I'm not sure. Haven't done these questions in a long time. Write an equation for the complete combustion of ethanol. Explain how the products of this reaction might differ in the reaction had been carried out in limited supply of oxygen. Okay, so firstly, complete combustion is the fuel in liquid form plus oxygen in gas form goes to carbon dioxide gas plus water liquid. Put a 2 here to balance out the carbons, put a 3 here to balance out the hydrogens, and now assess where we're at. Got 4 oxygens, got 7 oxygens on the left-hand side. We've got 3, so we need 4 more, or 7 in total on the left-hand side. So if I put a 3 there, I'll get 7 in total on the left-hand side. That looks good, just double checking, that all looks good. Now I got to explain what the reactions, how the reaction, if there is not enough oxygen, then you will, I don't know why I'm writing this, you will still get water formed. So what I'm trying to say is water is like the preferred one that oxygen goes to, and then if there isn't, you'll get these carbon monoxide and carbon soot. But carbon monoxide and or solid will be formed. And that's more of an identify layer, so I probably should give one extra bit of statement to give a reason why, because it is an explain level, although it is 2 marks, it probably could just get away with it. This is because at the reaction site, there is not enough oxygen particles present for the 1:3 ratio needed for complete combustion. And if you go right out the equations that don't involve, like if I wrote carbon monoxide, you'll see the ratio between fuel and oxygen to be less. You don't need as much oxygen to get carbon monoxide. You don't need as much oxygen to get carbon soot. In real life, you'll probably have a mixture of all the types of all 3 reactions happening at once. Okay, which reagent or reactant is in excess? Show your calculations and hence determine the amount of moles of the reagent identified as being in excess. Okay. Right, we've got to figure out how many particles do we have of ethanol, how many particles do we have of oxygen, put them in the context of their 1:3 ratio, which is their stoichiometry, and assess which one's going to be left over and how much of it. So moles, it's a lot going on for 2 marks actually. C2H6O equals, what information I get its mass, so it's mass on molar mass, 5.85 on, I'm going to draw that in the middle because I'm going to have a pretty long molar mass. I'm looking at 2 times 12.01 plus 6 times 1.008 plus 16, and that's going to give me 5.85 divided by 2 times 12.01 plus 6 times 1.008 plus 16 gives me 0.12698. 6 is good enough. And I'm going to need some space. I'm going to jam it up. Moles of other reactant, which is oxygen, equals also mass on molar mass, which is not going to be as long, so 14.02 over 2 times 16. That's going to equal 14.02 times 2 divided by 2 times 16. Sorry, it's the wrong 14.01 divided by 32. 0.4378125. Okay, so for all the fuel to react, I'm going to need to have 3 times, oxygen would need to be 3 times that. So I'm just like quickly assessing that oxygen is going to be the one that's in excess, and I just got to basically state it. So as 3 times the moles of C2H6O is less than, sorry, as 3, what do I got to say? So I got to say, yeah, sorry, I was doing the right things. 3 times C2 is less than the amount of particles that are maximum moles of oxygen. So basically this is how much oxygen you would need, and this is how much you have. Ethanol is limiting reagent. The number of moles of oxygen in excess would be equal to the 0.4378125 minus 3 times 0.126986, which equals minus 3 times 0.12686 is 0.05685 and 45, I should say. And then sig figs, what do I got? I got all my answers are in 3 sig figs. Oh, sorry, all the numbers I'm using are in 3 sig figs. So I'm going to express my answer in 3 sig figs, which would be 0.0569 mole. Okay. In order to carry out an investigation, the student obtains 2.5 moles per litre standard solution of sodium carbonate. 20 mils of that standard solution is diluted to 100 ml in volumetric flask. Okay, so it's a dilution. Calculate the concentration. If you don't know, this is using a dilution formula which works on the idea that the number of particles of sodium carbonate at the start of the dilution and at the end of the dilution, like all I'm doing is putting 20 mils in and then adding it up to and adding water up to that. So the number of moles hasn't changed. Okay, so the number of particles hasn't changed. All that's happened is the amount of volume has changed. So the formula is this. C1V1 equals C2V2 is the dilution formula. And my concentration, so I'm trying to find my N concentration, which is C2. So it's going to be C1V1 divided by V2. My concentration initially was 2.5 moles per litre. My volume was 20 mils, so 0.02. And my final volume is 100 mils. And this should be, for me, this is just identifying that this is diluting by a factor of 5. So I'm expecting 2.5 divided by 5 is 0.5. And really it's just a ratio of that. So 0.02 on 0.1 is 1/5. And so I'm basically just dividing by 5. All right, and that's moles per litre. And that's my answer to technically 1 sig fig, although not really. That, like, this has 2, this is vague 1 or 3, this is vague 1 or 2. Don't really want to go into this too much. Let's just leave our answer like that. I already have done this. Okay, this is left there from a while ago. The dilute solution is basically write the balance of chemical equation. Looks like a acid plus a metal carbonate. This is a metal carbonate. This is your acid. Goes to your salt plus water plus carbon dioxide. Excellent. Okay. And looks like a doubling up of questions. Determine the mass of sodium sulfate that can be produced from the 20 mils of sodium carbonate used in this reaction. Okay. It's all 1-to-1 ratio, so I need to figure out the number of moles of sodium sulfate. And I'm going to get my information from sodium carbonate. So moles of sodium sulfate. I'm just going to get that information from moles of the sodium carbonate. My moles of sodium carbonate I'm going to get from C times V. And the constant says used in this reaction, and the reaction was used from a diluted solution was reacted. So we're going to use the 0.5 that we just calculated and do 20 mils of that, and that's half of 0.5 is half, so I'm going to go 0.01. And then I got mass, so I'm just going to convert that to mass. So mass of sodium sulfate equals N times molar mass equals 0.01 times 22.99 plus sulfur 32.07 plus 4 times 16. Chuck that in my calculator. 0.01 times 22.99 plus 32.07 plus 4 times 16. 1.1906. 1.1906 grams. And 2 sig fig. Sig fig would make that just 1 gram. It's not a great question for sig figs. I guess technically we're going to go one sig fig if you wanted to be crude about it. Sure, 1 gram would not be a sig fig question. All right, last question. Compound contains carbon, hydrogen, and nitrogen. Combustion of this compound produces that much water and that much carbon dioxide. Calculate the number of moles of carbon dioxide in water. Okay. Moles of CO2 equals mass on molar mass equals 0.279 on 12.01 plus 2 times 16 equals 279 divided by 12.01 plus 32. I get 0.00633394. That's enough decimal places. Moles of water is going to be mass on molar mass equals 0.172 on 2 times 1.008 plus 16. So it's 0.172 divided by 18.016 is 0.00954.706 mole. So they want us to find the mass percentages of carbon, hydrogen, and nitrogen, hence the empirical formula. Right. So I need to know, normally approach this by going, I need like the ratio of carbon to hydrogen to nitrogen. I need to know its mass, its molar mass, its moles, and then I want to divide it by the lowest moles, and that gives me the ratio, the lowest ratio they come together, which is the empirical formula. So firstly, I'm just going to tackle like this. I know that, I know him, and I know him. What bits of information do I know from part A? So I know the moles of carbon dioxide, which is going to give me the moles of carbon, 1-to-1 ratio. So I know the moles of carbon. Moles of carbon is just going to be 0.00633394. Moles of hydrogen actually just going to be double the moles of water. If for every 1 water, I get 2 hydrogen. Sorry, I just have a mental blank there. So 2 times that is 0.0954706 times 2 is 0.01909.412. Right, so I can't work out moles yet, but I can work out that and that. And then I know the total equals 0.125, so I can work out that, which will give me that. Great. Okay, that's my order. Right, so firstly, carbon's mass. So 0.063394 times by 12.01. Sorry, not times. Yeah. Yep, sorry. It's going to be N times molar mass. So 0.0761361. Do that for hydrogen, which is annoying because it pretty much spit out the same answer. 9412 times 1.08. Slightly changed. 2468. And so if I go 0.125 minus those two numbers, I should have the mass of nitrogen in my sample, in my compound, 361. And that gives me 0.02967. Divide that by 14.01. and that gives me 0.0021139. And now I divide all these numbers by the lowest the lowest moles. So divide by 0.02 for all of them, I guess. And that would give me 1. 2 goes into that. Oh, I have to do it on my calculator. No, it'd be 9. Do 9. That would be 3. And that's my answer. Yeah, that's my answer. Does that answer the question? I got the empirical formula. Find the mass percentage. Okay. Oh, that seems a bit silly. So it's just a roundabout way. So what they want you to do, silly way. So what they want you to do is find the mass of carbon in your sample. So if you got the mass of carbon is like, say, the 0.761361, and that makes up X percentage of 0.0761361 divided by 0.125 times 500. So, oh, sorry, it's actually 0.076. Which actually gives me 60.9%. And then if you had a 100 gram sample, you can just turn that into 60.9 in 100 gram sample. And then you divide it by its molar mass and you get some kind of answer which looks like 5-ish. So 60 divided by 12.01, which is 5.07. Oh, how annoying. Because then you got to do it for all of them and you'll get some mole answers, or you get some answers, mole answers, and then you divide it by the lowest moles and you should do it. So I'm going to have to confirm that. So mass of hydrogen equals 0.0192468 divided by 0.125 times by 100% equals some kind of percentage that I will convert into mass. This is so stupid. 192468 divided by 0.125 times by 100% gives me 15.3%, which is 15.3 grams in 100 grams divided by 1.008, which basically just equals 15.3. I'm getting lazy. Mass of nitrogen equals 0.029617 divided by the mass total divided by times by 100%. 0.029617 times divided by 0.125 times by 100 gives me 23.69% equals 23.69 divided by 14.01 equals 1.69. And lo and behold, if you divide them all by 1.69, should get 1. 1.69 should get 9. Times by 9. Yep. And that should give you 3. Okay, so this is the stupid way, and that's the way it should be done. Unfortunately, this is the way you needed to go.